Okay.
What does that even mean?
Right here. What forces are acting on Tarzan? Gravity, straight down, and tension. Acting at whatever angle. Okay? Gravity is a conservative or non-conservative force? Conservative, so we're good.
Constant force that's in the universe.
Okay. And tension, is that a conservative or non-conservative force? Non-conservative, like, that's not good. But, which way is Tarzan moving at this moment in time? We're going to say that direction. So, like, how would we describe that? Like, academically, we would say tangent to the circular path. Okay.
It's circular, but
Okay.
really he's moving perpendicular to gravity.
So, notice that that is perpendicular to tension. Okay. Here's the takeaway. If you ever have something moving in a circular path, like an arc or whatever, the force that's causing that to happen is acting perpendicular to the way it's moving. No work is being done by that force. So, is mechanical energy conserved? It is. There is no non-conservative forces doing work. Okay.
You know, that actually, the swing actually reminds me of that one scene from episode 4 in Star Wars where Luke and Leia are in one of those canyon shafts and they have to swing across.
Yep.
Because the bridge wasn't working.
Yeah.
Oh my god, that was an intense blaster fight.
Okay. So I want to walk through how to do a energy bar graph just because I think it'd be beneficial. So, initial final.
Do you want this?
Do you want to see that one? I'm going to make the lowest point I care about equal to ground zero. Okay. Now, initially, did they have kinetic energy? No. No, this is a pretty lame one. I'm not going to do this one. Sorry. I want more complicated. I want this one. We did this on Friday.
Yeah.
I'm going back to yeah. So, initial, final, ground zero, lowest point we care about. Yes? Okay. Initially, does it have kinetic energy? Yes. It's moved. Why? Because it's moving. How many pennies should I give it? It really doesn't matter. You're making this up. I'm going to say because it's moving 1 meter a second, that seems kind of slow. I'm going to give it 1 penny. Could you give it 2? Sure. Doesn't matter. Okay. At this location, is it above ground zero?
Yes.
Yes. So it has potential energy. How much? I don't know. Give something. Like, sure, 5. Why not? Something. Here's where it starts mattering. The relationships. Your savings plus your your checking plus your savings is going to give you your total money in the bank. This makes a difference. So you take this and you give yourself 6 pennies because that's how many are in the bank. This relationship makes a difference. Matters. Okay? Now,
So it doesn't matter like whether kinetic or potential energy has more.
Correct. It does not matter which one has more. All that matters is, does it exist, and does this plus this give you that? That's what matters. Okay. through the process from initial to final, was there any work being done by non-exerted forces? Yeah, friction's doing negative 3,000 joules of work. How many should I take away? Well, don't take away 6, that would be silly. But take away something less. Okay, sure, we could do 3, does not matter. We could do 1, we could do 2. You could do,
Possibly, so we
Okay.
could do like,
so at the end, we've got
ouch.
6 minus 3 gives us 3 left. Actually, what I'm gonna do, take away 2, just so we don't make bad connections. Okay? So I have 4, I took away 2, I have 4 left over. At the end, all my kinetic energy, my mechanical energy, I'm at ground zero, so I have no potential energy, so all my money is in the checking account. So I'm kind of reverse engineering that.
Pretty much.
So this plus this equals that. That's the third relationship that must hold up. Okay? How we feeling about that? Okay? And so what that enables us to do, so
I was, so like I did all the homework from last night, when they're like equal,
Yeah.
does that matter if you have like one more than the other? Or like how are you supposed to know when?
great question. It doesn't matter. Okay? So this chart enables us to answer questions like this. Tell your neighbor.
Oh, wait, never mind.
Yes.
Okay, correct answer is? Correct answer is B. Kinetic energy gained, went from 1 to 4, gained 3. Potential energy went from 5 to 0, lost 5. Kinetic energy gained less than potential energy lost. Good? Okay. All right. Colored tracks. Which one do you think's gonna win the race?
This is gonna be. I already know this one because I've seen this experiment happen all over the place.
Probably yellow.
Yeah. Okay, everybody have their votes? Oh, boo hiss. Eddie, can you turn the camera? Tilt it down a little bit. Okay. Everybody have a vote? 3, 2, 1. Blue, yellow, green.
Now they're running all over the place.
Which one won? Blue. All right. Blue sped up sooner in the race? Okay with that? Okay. Follow-up question is, we know that the blue wins, but when they reach here at the end, which one's crossing the finish line traveling the fastest speed?
Red.
Okay, everybody have a guess? What we're gonna do is we're going to see distance-wise how far it goes. Does that make sense? Yeah. So here is blue. Catch those right there. Okay.
How can the camera see?
Yellow. Got the same green.
Same.
Red.
And again.
Huh. That's funny. They all hit about the same spot. Why is that? Is mechanical energy conserved? Is there any non-conservative forces doing work?
Yeah.
The only thing that's present in existence is friction.
Okay, so friction, it's rolling. We're gonna say no work being done by that. You okay with that? It's rolling. So, mechanical energy is conserved. You got normal force and gravity. Normal force is acting perpendicular. So, the kinetic energy it had, the potential energy it had up top is equal to the kinetic energy it has on the bottom. Good with that? Here's the takeaway. If mechanical energy is conserved, then the path taken to go from your initial to your final does not matter. Okay? They all have the same speed at the end. Okay? Now, it's also important to know what your principles, what limitations they have. So work and energy cannot tell us anything about who wins the race. It cannot tell us chronological, anything that's time-based. I mean, if you look at your equations, there's no time in there. There's speed and there's height, but no time. Okay? But what work and energy does really well is relates how speed and height go together, how they're related. Go with that? Okay. So falls apart with like the timing of it, but does a great job related to speed and height. Okay? I want to jump to this question here. Okay. So, if a 2,000 kilogram truck is going 40 meters a second up a 30-degree runaway truck ramp, how fast is it going after 100 meters if there's 5,000 newtons of friction acting on it? Okay. So, step one, we're going to pick our initial, final locations. Initial and final is going to be 100 meters past that. Okay. Step two, lowest point we care about, down here, we make that ground zero. Step three, figure out what energies we have. So I'm writing my original equation. Initial kinetic plus initial potential plus the work done by your non-conservative force is equal to your final kinetic plus your final potential. I want you to mentally cross out which ones you don't need.
Stop. After 100 meters, if you were basically going down like one of those canyons I found in the Southwest.
Assuming how fast. Okay. Give me a thumbs up if to keep it, thumbs down to cancel it. Initial kinetic energy, thumbs up, thumbs down. Thumbs up, you're moving. Kinetic energy initial, thumbs up, thumbs down. Keep it, cancel it. At the initial, you are at ground zero. Potential energy is 0. Work done by non-conservative force. Keep it or cancel it. You have friction doing work. Keep it. Kinetic energy initial, final. Keep it. Cancel it. How fast are you going? We need to keep that. If it has speed in it. Okay, potential energy. The final. Thumbs up, thumbs down. You're above ground zero. Keep it. So we have 1/2 mass times speed squared initial plus, is friction doing positive or negative work? Negative. Okay, so I've got negative work is equal to 1/2 mass times speed squared final plus mgh final. Can you cancel masses?
No.
Can you cancel masses? No, you don't have a mass in every expression. Okay? Question. Can I stick 5,000 in for work done by your non-conservative force?
Yes.
What unit is 5,000 newtons? What unit is that of? Force. You need it in what? Joules. Stink. How do I figure out? Okay, so this is where you do work is equal to force times distance. You okay with that? Okay, so this becomes force of friction times distance is the work done by your non-conservative force. Okay, this is super popular here. Okay, not doing this.
Is this like the time where the degrees don't matter?
Good question. Hang on to that thought. Okay, so we have 1/2 times 2,000 kilograms times 40 meters per second, and square that minus 5,000 newtons times 100 meters. Everybody good with that?
Yeah.
Right here, forgetting to multiply that by 100 meters, that's going to be a popularly missed multiple choice.
Wow, that screwed up.
Okay, because you forget, you're like, oh look, 5,000, boom. Okay, it's equal to 1/2, 2,000 kilograms, final speed squared. Hang on, this is really important. 2,000 kilograms times 9.8 times height. What's my height? What's my height?
Figure it out.
You need this dimension here. Height above ground zero. How do we find that?
Sine 30.
We go sine of 30 is equal to 100, h over 100. Woo! Okay? So this ends up being 50 meters, and your answer is 10 For 9, get it in seconds.
Here's my homework.